Okay, we should probably get started. Listen, a couple people yet? This is where we've sort of been talking about bands, how they arise from the overlap of molecular orbitals as all these atoms are atomic orbitals. As all the atoms get closer and closer together, we get these what we call bands arise. And for a conduction, something that's a conductor, the valence band and conduction band just may basically overlap, or you have room in your valence band to move energy, electron energies up. So they can gain energy and get kinetic energy. That's what they require to start moving. So that's what you should keep in mind. What we're talking about here is electrons in valence band need to be able to gain energy to be mobile, to move, have a current. So, valence electrons must be able to acquire kinetic energy when you start moving. I.e. produce a current. So the difference between a conductor and either an insulator or a semiconductor is there's a gap, a forbidden region where you don't have any energy levels between the valence band and a conduction band. Okay, so this conduction band is empty, and also the valence bands are full. So there's just no room. I have an electron that has this much energy, or one that has lower energy. Remember, energy is going on this scale. So you have electrons that have lower energy. They have everything's filled. They don't have a place to go up and gain energy. Okay. And the electron at the top of the valence band can't gain any more energy because there's nothing here. It's a forbidden area. Okay? They would have to overcome this energy gap to acquire energy. And that's usually a lot of work to do that. Okay? Semiconductor, the gap's not quite as big. So you can sometimes, with a little help, get the electrons up there, okay? And it's the semiconductor we kind of want to focus on here for today. So I just want to talk about p-n junctions. Maybe we'll start talking about transistors, but might be kind of a short day, we'll see. Okay. By the way, let's talk about putting impurities in a semiconductor. So when we add a semiconductor, semiconductors are things like germanium, silicon, and those are the two main ones that we think about when we think about semiconductors. So if you look at, let's pick germanium. The electron configuration looks like this. It looks just like an argon atom, which has 18 electrons, and then you have to add on 10 that can be in the 3D state. Then you go to the 4s, and there's 2 you can put in there. And then in the 4p state, you only have 3. Okay. You can have 6 in there. So it forms covalent bonds with other germanium atoms. So this is going to be my representation of a bunch of germanium atoms in a nice regular array. Okay. What we're going to do is take out one of these. So it's making all these bonds, and then each atom's getting its full 4p state. Okay, it's sharing 3 electrons with other. So it's actually making 6 covalent bonds with other germanium atoms. Okay. Now, all of its electrons are being used for covalent bonds. Everything, it's all happy. But what if we take one of these and we replace one germanium atom with, let's say, arsenic. So if you take an arsenic atom, arsenic has this electron configuration. It's almost the same. It's right next to germanium on the periodic table. Actually, I got germanium wrong. Germanium's smaller than arsenic. So. It's one to the right on the periodic table from germanium. So it has this configuration. So it has one more electron, okay? So we have all these germanium atoms in there, and they're all sharing their electrons. They're N equals 4 electrons, making covalent bonds. And then suddenly you put in this other arsenic atom, and it has an extra electron. That electron doesn't know what to do, because all the other electrons are being shared, and it doesn't really have a place to go. Okay? So, has an extra electron. Not shared in covalent bonds. So by introducing this arsenic, you get this little extra electron in here. It's not really tied to any nucleus. So it could jump around from place to place. Okay? So it's fairly mobile. So what we do, so every arsenic atom that we put in here instead of a germanium gives us one of these electrons that's not really tied, okay, to any nucleus. it doesn't take much to move it away from its arsenic atom that it was at. Okay. So actually what that does, by the way, if we have a semiconductor, what we're doing is this. We had this when we had all germanium atoms. Now we have this electron that doesn't take much to get it away from this and make it mobile. Okay? What that does is introduce an energy level, basically. If you're thinking of energies here, it gives you this one energy level that's really close to the conduction band. It's got an electron in it. Okay? So what that does is, by drawing it right under the conduction band, what I'm saying is it doesn't take much energy to get it up to the conduction band, make it mobile. Okay? So, doesn't take much energy to, let's call it delocalize that electron, meaning it's not localized around the nucleus. Delocalize electron and make it mobile. So by doing that, we're saying, look, it had an energy, it must be right under the conduction band. We give it a little bit of energy, it can move around. So it's a conducting electron at that point. Is that, are you okay with that? Does that make any sense? So we don't, of course, just replace one germanium with an arsenic. We replace many germanium. Not too much, but we call it doping. So we put in roughly, it might be 10 to the 25th atoms per centimeter cubed. The density, though, if you look at the density of a solid, what do you think that might be? You guys remember that at all? Calculate it. Well, the density might be 10 to the 28 atoms or so per centimeter cube. So you're not putting a lot in there, even though it seems like a lot, right? You're not replacing a whole lot of the germanium atoms, just some. And they have techniques to do that. I'm not an expert at that. I don't know exactly how they do it. It involves putting this stuff in an oven and introducing your arsenic and waiting for a while. And maybe putting it under pressure and stuff, okay? But anyway, they call it doping. So you're introducing a whole bunch of electrons that can get up to the conduction band pretty easy. We give them a little energy, okay? So we call this an N-type semiconductor because we introduce negative charges that are going to be able to get into the conduction band. And we call these donor levels because we donated an energy level to the, well, I don't call them that, that's what the solid state physicists call it. So that produces what we call an N-type. That means you can put negative charges up there pretty easily and have conduction. Much easier than this. You'd have to give them 1 eV of energy to get up the conduction band. Here, we're talking about the energy level, the change in energy per there is between the donor levels and the conduction band is on the order of maybe 0.1 eV or so. And it's such that, do you remember what you have room temperature? Do you remember what that has units of energy? Do you remember what that is, roughly? T equals 300K. You used it on the last test. You better remember.
5 point? No.
No?
That was something else.
It's like 0.026 eV. But the point is, we call that a thermal energy. Okay? Electrons can acquire that much energy just because of the temperature. It turns out some of these are close enough that electrons can just jump up there just acquiring thermal energy. Okay, and get up there. So there's a probability just from thermal energy that they'll jump up to that conduction band. You don't even have to give them energy. And if you're going to give them energy, how are you going to give them energy? Get up there. What do? Put an electric field in your conductor. You hook it up to a battery. You'll give them energy. Okay. So that's making an N-type semiconductor. You take your semiconductor material like germanium and you put impurities that are to the right of it on the periodic table, have an extra electron. So what if we go the other way? So I'll take germanium again, I guess. See if I use germanium in my notes. I guess I don't have notes for this one. That's weird. I don't have that. Well, anyway, let's make an example. Let's take germanium. Germanium again. Again, the electron configuration is this. And now we're going to replace one of the germanium atoms with something to the left of it on the periodic table. So it has one less electron. So it might be gallium. Okay. So now we had germanium, everybody had covalent bonds between all the nearest neighbors. Everything was happy. And now you replace it with something, there's one less electron to make covalent bonds. Okay? One less electron. To make covalent bonds. So what's going to happen? You're going to have a place there that if we had an extra electron, we could put it in there and be happy, right? So we create a vacancy of an electron, and we'll call it, well, it'll act like a positive charge, okay? We have a name for it, we call it a hole. Sort of an electron hole. The electron would like to go in there, okay? It's a vacancy. An electron would like to go in there. a location, and the electron would like to occupy this space, okay? So you think of it as you've got this terrain, you've got this surface, you got your electrons that might be rolling around there, and if it reaches this hole, it would like to go in there and just sit there, okay? But it's a very shallow hole, okay? The electron that might go in there could go out, okay? I mean, electrons are not going to be extremely attracted to this place, okay? Now, let's say an electron does fill this. Electron goes to this space. So we have an electron here, maybe, and maybe it occupies that space. What happens there? Then that electron moved from the space it was, and it created a hole where it was, okay? So if an electron moves, fills the hole, then it creates a hole where it was. Okay. So what happens is that you can have these, here's my atoms. You can have an electron move over here, fill this, creates a hole there, okay? And then you can have an electron move over there, fill that hole, and creates a hole here. So what it looks like is that you have, this is a hole, it looks like you have this positive charge moving this way. So the effect is a positive charge going this way, even though electrons are jumping this way, okay? So electrons filling holes has the effect of a positive charge moving around. So you're allowing, basically, in reality, what you're doing is you have a place for electrons to jump, to acquire a little energy. Maybe it could jump, another one could jump to a hole. So as far as if you look at energy levels for this kind of thing, if we draw our conduction band and our valence band again, give the electron a little bit, it has a place to have a little bit of energy. It can move up from its location and go into a hole with a little higher energy there. So these are empty spaces we put in here by putting the gallium there that's right above the valence band, okay? So we create energy levels right above valence. Now this isn't going to make a good conductor at all. You can have an electron that's down here, it can acquire a little bit of energy. So you have so many electrons can acquire just a little bit of energy by doing this, okay? Can't acquire an infinite amount of energy, but they can acquire a little energy. So electrons can acquire a little energy. So we call this type of doping, we call this creating a p-type semiconductor, because it's the effect is positive charge moving around in the semiconductor, okay? So this creates a p-type semiconductor. So again, it's the idea of these holes as being, thinking of them as real positive particles moving around the semiconductor. That actually comes from Dirac. Okay. So it creates a p-type semiconductor, positive mobile charges. What we call holes. Okay. Again, for all effective purposes, the hole acts like a real particle with some kind of effective mass. Okay. But in reality, what's happening is electrons are jumping from vacancy to vacancy. But it looks like that vacancy is moving around. Okay? So the holes are vacancies act as particles have, since they're not real particles, they act like them. They have some what we call effective mass. It's an effective mass because they take time to go from place to place to place. Okay. So of course, if you have these holes, if you put in an electric field here that goes, if the electric field goes this way, if you put one in there, electric field, negatively charged particles like to go opposite the electric field. Positive charged particles like to go in the direction. That's how we test for electric field, right? The positive test charge goes in the direction of the electric field. So the electrons would tend, if you put an electric field in this semiconductor, the electrons would tend to jump over this way, your holes would go that way faster. Okay? But they can only go so fast. Once you make the electric field any bigger, it doesn't really help things. They're sort of restricted because it's the electrons finding the holes going the other way. And the electrons have a lot of collisions when they do that, when they're moving around and so forth. So making a stronger electric field doesn't necessarily make the electrons go that much faster from place to place, right? Okay, so that's creating a p-type, creating an n-type. What I want you to remember from this is that if you take what we call a semiconductor and you put in something that's to the right on the periodic table, it has an extra electron, you create the n-type. And if you put in something to the left in the periodic table, it has one less electron for the impurity, and you create p-type. Okay, so what can you do with this now? This is not a very good conductor. The n-type makes a better conductor, but you're still limited to how many conduction electrons you're going to have by how many impurity atoms you put in there. But what we do is we put these two together. We put an n-type together and a p-type together. What good does that do you? Well, we make a switch that works very fast. Little energy. Okay? It's called a p-n junction. That's what it is. It's a switch. Okay? Electronic switch that uses very little energy. So before the p-n junction, which we'll call a diode, if we're thinking of it as this, what it does is restricts the current. Current can only go one way through the diode. And if you reverse the polarity, so you put a diode on a battery, hook it up right, you get current. If you hook it up, change the polarity, you get no current. So that's a switch. Okay? So before that, to make switches, we had vacuum tubes. Vacuum tubes basically have a filament in there, and electrons boil off. So they're hot. So they produce a lot of wasted energy, goes into thermal energy. So they're inefficient. They're also big compared to what these diodes are. So we make diodes on your computer chip. You have lots and lots and lots of diodes that are miniaturized. Here's a bigger, I brought some in. Chop all in my hands, but I don't know if I have enough here. So you can see. Pass it up. So that's what a diode, it looks like a little resistor, right? So one of the things you'll notice on that diode, if you look really carefully, so they come in different configurations, but it'll probably have, if you look really closely towards one end, it'll have a little band on it, little gray band. You can barely see it on these, okay? But I'll explain what that is for in a minute, okay? It's going to tell you what type of semiconductor that is on that side. So you're going to put the PN together, and this is going to be the N type that's close to this band. This is going to be the P type. It's in there. Okay. So another electronic symbol for this. So this is diode. Electronic symbol would look like this. And this is your, so this is called the cathode side. This is called the anode. This is the anode. And this is the cathode right here. So let's talk about what happens when you put a P-type and N-type, squeeze them together somehow, combine them. So the diodes you have there are just made for us when we want to make stuff and have current going a certain direction, and they don't handle a lot of voltage or a lot of current, the ones you have. They make some that if you want to handle a lot of current, power diodes, they look a lot different, a lot bigger, and some are made for high voltage and stuff like that. So, but the basic idea is this. Here's my P, here's my N, and here's the junction. So this is called a PN junction, okay? Let me draw this a little bigger here. So here's my junction here. Let's say this is the N-type. Here's my P-type, okay? So the mobile charges in the N-type, the things that are, the particles that are able to move are electrons, right? So have mobile negative charges, charged particles. Over here you have holes. These are the things we're thinking about as moving around the material, okay? Now, this is an important thing here is each side, the N-type side and the P-type side, they're electrically neutral. We don't have any excess positive charge versus negative charge. When we doped, we put an arsenic in there, we had that extra electron, it was still electrically neutral. That arsenic atom is electrically neutral, okay? So both sides are still electrically neutral. That's the key point. Okay. Now, what might happen, so we've got these things very close together. Okay, there's this good interface between them. Meaning particles could maybe get over from one side to the other. Okay. Well, if you have a positive charge here and a negative charge here, they like to combine, right? So the electrons, which are much more easily movable, is the electrons that actually really move. What will happen is you'll get electrons combine the holes at the interface. Okay? So they'll jump over that boundary and combine with the holes. They like to be in that hole, they'll go over there. But what happens when you do that? When that happens, you had an electron on this whole side was electrically neutral. But now if an electron jumps over there, this side has a net positive charge, right? It creates a net positive charge on the end. And then we have, and on top of that, we have an extra electron on this side now, if that electron moved over here. So, and a net negative charge on P side. Okay? So now, we're saying we have a net negative charge over here and a net in the vicinity of this interface. That creates an electric field. Like you have parallel plates, if I have a negative charge on one plate, positive charge on the other plate, I have an electric field between there. So that's going to set up an electric field in this region. And the direction of the electric field goes from positive to negative, right? Does it go negative, positive? What does it do? You want to put the positive test charge, it's the direction it would go. So it's going to set up an electric field here. Okay, so it sets up electric field in region of the junction of the interface. Okay? Well, what's that going to do? Well, electrons want to go opposite of the electric field. Positive charges want to go in the direction of the electric field. So eventually, that electric field is going to be big enough that no more electrons can jump over, because they want to go the opposite way. Okay? So this electric field that's set up by this gets so big that no more electrons can combine with holes. So an E field is set up around interface. Eventually, it's big enough to keep any more electrons from going over. So it keeps electrons from crossing the interface. So what the solid state physicist then will say is you have a region around that interface now where you don't have any mobile particles, any particles that are free to move. So here's your interface. N-type, P p-type, in this region, there are no mobile parts. There's no electrons that are free to move. There's no holes free to move because they've all combined, okay? And we say there's an electric field set up in here. And we call this a depletion region, meaning no mobile charge carriers. In this region. So then it stops. Very quickly, you put these two together, you get electrons jump over, fill these holes, then you set up an electric field in there because now you have net positive charge here and net negative charge over there, and now no more electrons can get over. Okay? Well, what do? Well, we hook a battery up. Okay? So let's connect a battery. Let's think of two ways to connect it. So I'm going to put the negative side of the battery on the connected to the P side, positive side of the battery attached here. Okay. This is called reverse biasing. And we'll call this battery voltage V sub B for biasing voltage. Okay? Here's my junction between the N-type and P-type. What's going to happen now is what I want to think about. I have this depletion region when I don't have anything hooked up. Okay, that's fixed. I've not done any, I haven't hooked a battery up or anything. This just happens when you put the PN and N-type together. Okay? Electrons can get across the barrier, so they do that, sets up that electric field, and then it stops. So you have this depletion region. What's going to happen if I hook up a battery like this? These are positive mobile charges on this side. I still have my depletion region, but over here I have positive mobile charges. They like to move. They're attracted to the negative side over here, right, with battery. What happens to the negative mobile charges over here? They're attracted to the positive side over there. So what's going to happen is you're going to get positive mobile charges collect on this side. Okay. And negative charges collect on this side. Maybe some of them flow around. Holes collect on this side. That means you had this depletion region, but now some of these mobile charges that were here, they've moved over because they're attracted to this positive side. So they're more congested now over here, okay? Now when it does that, if the mobile charges are moving over here, we're going to have this more positively charged because the whole thing was electrically neutral still, where we didn't have. So we've moved more of the positive charge here. It's going to make this even more negative here. And then the mobile electrons are going to congregate over here. And maybe some of them will flow a little bit. Maybe you'll get one or two flow around them. But what happens then, this is more positive again over here. You set up a bigger electric field in here eventually. depletion region gets bigger. Does current just flow along here now?
It would depend on which way the battery is, wouldn't it?
Well, yeah, that's what I'm saying, but this way, what's gonna happen? Think about it, think through this. If the positive charges are attracted to this side, and the negative charges are attracted to this side, won't you just get flow? What'll happen? And what would stop it? Is there any possible way to stop it? Where what you guys do a little thinking. Use your brain power a little bit. Think what's subtle about this? Is there anything? Is this gonna? So I said, yeah, you leave this area more negative charged, but the positive charges are all coming over here. This area is no longer neutral. You had all these positive charges that were mobile, that were over here. Now they're all congregating over here. Okay. And then the same thing over here. Now you got an excess of negative charges actually over here. So even though this area in here, yeah, this is more net negative, this is net positive. Over here, it's net negative and net positive. You're going to set up, eventually you're going to cancel out this electric field here. You're going to have so much negative charge here and so much positive charge here that they're not going to want to move anymore because it doesn't want any more positive charge to come this way. And these electrons don't want any more negative charge coming. They're crowding them already. Okay? So eventually, because now this is net negative and this is net positive, it's going to cancel out this electric field that is trying to push them. So think about what does this, another way to think about it is what is this doing? It's setting up an electric field in here. What direction is that electric field? Let's say. Well, that was pushing this even bigger this way. But these things are going to produce an electric field. That positive on this end. So I don't know what I want to call this. I'll call it E naught for a different electric field. Net negative on this end. It will eventually cancel out the electric field that's caused by this, trying to pull the charges this way, trying to pull the electrons this way. Eventually you get so much to accumulate here, they fight back. Okay. You get a balance. So you might get a little current at starts, but then when you get enough electrons over here, and there's an enormous amount. Okay, the Coulomb potential is really strong. Electrical force is really strong. So you're eventually going to get enough electrons over here. They're not going to let any more come. You might get a dribble of them, of stuff going across here, but you're going to set up an electric field here that counters that electric field. It's caused by this. Okay. So eventually, you get a balance between electric fields in there. And you get no or very little current. You might think, okay, so before I say the next thing, I want to make sure we're clear. You put this voltage on here, what you're really doing is creating this bigger electric field in here, trying to push the protons that, or the holes that way, and the electrons this way, okay? But that's not all there is. Now, because you've congregated a bunch of positive charges over here, this is net positive, more electrons over here, this is net negative, so you set up an opposite electric field that will very quickly cancel that out. And there's so many electrons available and stuff, you're not going to be able to overcome that. You're going to have a really high potential. Now you might put a big enough potential on here, you can overcome that, but it's not going to be useful to us. Okay? So basically you get no current. It starts a little bit, you might get a little dribble of current, and then it stops because of those competing electric fields in there. So reverse bias, which is we put a negative potential on the positive side, a positive potential on the negative side. That's why they call it reverse. That gives you no current. We don't expect any current. But if we go the opposite way, of course, that's when you're going to get the current. So what happens? So it's called forward biasing. My p-type, my n-type. So forward biasing, you put the positive side on the p-type, the negative potential on the negative side. This is our bias voltage. Again, now you produce an electric field from that battery in here. It's going this way. Let's call that, I should call that the bias electric field. That's what I should call that. So EB is bias electric field. Okay, so what is the effect that's going to have? You had this depletion region when you had no voltage on it, where there was no mobile charges. Now you put a battery on this, is going to create an electric field in here that goes this way. Okay? What's that going to do? That's going to push. Positive charges want to go in the direction of the electric field. Negative charges want to go in the opposite direction. So it's going to actually pull positive charges over this way, farther. And it's going to pull the electrons over this way. So the depletion region gets smaller than it was. So when we had no bias whatsoever, no voltage, we had a depletion region. If we put on, so we had a depletion region. If we put on a battery like this, we increase that area where there's no mobile charges. So we increase the depletion region. If we do this, we're going to decrease the depletion region. Okay? Now what's going to happen by decreasing that depletion region is some more electrons are available to jump over here. Okay? They can make it across this gap where there's no mobile charges. Because this is not drawn well, right? It gets very small. So the depletion region is small enough, electrons can cross over. And holes might be able to jump over the opposite way too. So what is our battery doing? It's supplying us with a supply of electrons, right? So we have electron that can jump over. Sometimes they jump over and don't combine with the holes and they go on over. But this gives us a new supply of electrons that are moving up here. So we get a current. So of course we think of the current as not electrons moving that way, but positive charges moving this way. But anyway, we do get a current. Now, how much of a current? Well, the mobile charges have to cross that junction, that interface, that depletion region. So let's estimate amount of current. So there's this energy gap, this area that has to cross over. They have to have so much energy to make it over that. Okay. So how are they going to gain that energy? They're gaining this energy from this potential you're putting in here. Okay. So the energy gain, let's look at the electrons. From the bias voltage. How much energy do they gain? So we have this bias voltage. The electrons, when you take a charged particle and you go through a potential difference, the charge times that potential difference is the energy that you gained. So it's equal to this. That's how much energy they get from that potential. Okay? So we expect the number of charges that would actually be able to make it across. It'll go like this. Depends on the number of electrons you have available. And then it's going to go as a Boltzmann constant. So this is the number of electrons available. So it looks like this. The number of holes that can go across the opposite way that also help with the current. Turns out the number of holes crossed are not really affected by this potential. Okay. There's still this constant potential difference in here. Let me see if how I can state that another way. Remember, the holes are not really, we think of them as positive particles moving, but the only way they move is if an electron jumps over it, fills a hole. So the rate that the holes move is completely independent of what voltage you put in there. And they move over at some constant rate. So the rate at which holes cross over is independent of the bias voltage. So we're talking about actual mobile holes suddenly going over to the other side. Now it will happen, it can happen, they're mobile. You can suddenly get a vacancy over here and lose one over here. But the rate that happens is a constant, okay? But it does depend on number of electrons available. So if the number of electrons that can jump over goes like this with the Boltzmann factor, but the number of holes that go depend on some constant, what that's going to lead to, if I had more time, we're out of time, so what this is going to lead to is the current due to the electrons is going to look like some constant depending on the number of electrons you have available. It's going to go like this. The total current is going to look like this. So I won't just put the electrons with the holes helping. It's going to look like I naught, and you're going to have because electrons are going one way, you get a current, the holes going the other way, it's like an opposite. So we'll talk a little more about this diode then next time. And we have a relationship between the current and this bias voltage. That's equation 1049 in your book. So you guys read 10.8 if you haven't read it. We'll talk about transistors next time, and read 10.9, superconductivity. So chapters 10.8, 10.9. I'm going to send you an email here with some homework problems over diodes. That'll be due Wednesday. Not a lot. That's it. The next exam. We haven't set that yet, have we? We're off. We're just going to talk about superconductivity. It's the only other thing in this chapter. Semiconductors, superconductivity. Pretty much be done with that next time. We're going to start nuclear physics. Nuclear physics is going to be on the final. It's not going to be on the next test. So why don't we set it for, let's give us some time to go back and review stuff. So it's going to be molecules and the semiconductor stuff. Why don't we set it for May 8th, a Wednesday?
Yeah.
How does that sound?
Yep.
And then we have a little time to finish chapter 11. We'll start chapter 11 before then. Okay, so let's set it for May 8th.
Time to go cram.
This test is going to be thanks.
So then how do you get LEDs?
LEDs are light emitting diodes. They're when a electron